Okay, so today we're talking just a little bit about parent functions. The actual lesson for today is the main topic is going to be linear graphing of linear inequalities, but this is a little reminder about parent functions. You guys know what x squared looks like, right? Generally, it's a parabola shape over 2 up 4. Tell me you've seen that kind of U shape before. Okay, good. Then that parabola there is based on some points. Like if I stick in -3 into there, remember that x is like a little empty parenthesis squared, and I drop in -3, what would I get for y? No, 3 squared is 9. How about 2 squared? 4. Notice they're positive because the negative times the negative makes it a positive. How about -1 squared? How about 0 squared? How about 1 squared? How about 2 squared? How about 3 squared? You see how that repeats? And that's because there's the symmetry here. Over 1, up 1, and over this way and up 1. All right, so there is some symmetry to this graph. This parent function, the parabola, I know you already know, but there's a couple others that we need to add to your repertoire. And the first one is square root. All right, so you got to know this one just like you know the parabola is that U-shaped thing. All right, well, the square root is generally looks kind of like this. Okay, it's kind of like a parabola buried in the sand. See the other part down here that you can't see because it's buried in the sand? Yes. Okay, it's like a sideways parabola. And let's see why. If I take zeros and I take the square root of 0, there is a simple answer. 0. So 0 goes with 0, and that's why it's on the graph. Next, if I stick in 1, what's the square root of 1? 1 goes with 1. So 1 comma 1 is on the graph. Next up, if I take the square root of 4, what do I get? 2. And I go over 4 and up 2. So I went a little high. I was just kind of generally showing you where it is, but over 4 up 2. And the next one is 9, over 9 and up 3. Over 9 up 3. So there is my parabola shape. It's sort of like a parabola buried in the sand. Okay, so that's what square root parent graph looks like. Would you make a sketch in your notes right now of x squared, which is the one we did before, and then square root of x? So here's x squared. Generally looks like that. Square root of x generally looks like that, like a parabola, sideways parabola, buried in the sand. Can't see the bottom part. Why doesn't it go down in the negatives? Because you'd have to stick in negative, you'd have to get a negative out when you stick in +1. That doesn't make any sense, okay? And how about this? Why doesn't it go to the left and like, instead of being like a buried parabola, why doesn't it look kind of like a seagull? Because you can't stick in -1 for x. Because why? Because if I stick a negative underneath the square root, that's not allowed. So I can't have stuff over here, and I can't have stuff down here. It's only going to be in the first quadrant there. All right, so there is square root of x. Now, who had a question? I saw a hand. Maybe I already answered it. Okay, moving on. Then there's absolute value of x. Make a little tiny sketch of this one. And we'll just stick in some points quick and figure it out. If I stick in -3 in for x, then what is the absolute value of that? What's the absolute value of -2? How about the absolute value of -1? How about the absolute value of 0? How about the absolute value of 1? 2? 3? All right. So then, yeah, exactly. It's a V. It goes like this. So it's sort of like a parabola, except it doesn't have the curves. It's just exactly straight lines. Okay? So that is a parent function. Now, why do we call them parent functions? That sort of implies that they have children. Do they like... No, we're not even going to talk about that. Okay. How do the parent functions have children? Well, they just have other functions that look a lot like them. Would you agree that you sort of have some traits that your parents have? And I know you may not even like to think about that, but it's true. You probably have some parent traits that your parents have. You know, maybe you've got your mother's eyes, or maybe you've got, you know, your dad's body shape, or maybe you've got your whatever it is, okay? You're going to have some traits that look like your parents. And so along those same lines, if I have a graph that's like y equals absolute value of x plus 4, I know it's going to be kind of a V shape. Okay, it's just might be changed a little bit. Just like you're going to be a little different than your parents. The absolute value of x plus 4 would be related to this v. It's just probably going to be moved somewhere, or maybe it's stretched a little bit. Okay, all right. That is the basics of parent functions, and we're going to talk more about in-depth stuff tomorrow about like domain and range. What do those mean? Hopefully you remember domain is the x's and the range is the y's. And we're talking about what x's would work in certain functions and which ones wouldn't. We already talked about that with the square root. Can't have negatives for x's. That means the domain, that's the x's, is only positive numbers. So we'll talk more about that tomorrow. All right, solving linear inequalities review. If you were going to solve this anytime you're solving it, solve like a normal equation, except if in the last step, or I would even say by any step, you ever divide or multiply by a negative number, you have to flip the sign. Okay, so if you're ever solving one of these and you find yourself multiplying by a negative or dividing by a negative, the sign has to change. Here's the simplest case. Negative 2x is greater than or equal to 4. If I divide this by negative 2, I have x, and I have to switch the sign. Is dividing by negative 2, negative 2. If you ever multiply or divide by a negative, switch the sign. Now, did I say if the problem has a negative in it, you have to flip the sign? No, that's not what I said. I said if you ever multiply or divide by a negative on both sides when you're solving it, that's when you switch the sign. All right, would you please take this one, multiply it out, solve it so you get all the x's onto one side and say x is less than 5 or whatever it comes out to be. Go ahead and try that one. I'm going to hit pause while you do that. Okay, I'm back from the pause now, and here we go. First I go 5x plus 7 because there was nothing to do over there. Greater than or equal to 2x minus 8. So I multiplied it all out. Now I get rid of the smaller of the two x's. May not seem sometimes it may not seem like that's the best way to go, but it always is. If you get rid of the smaller one, you're left with a positive number of x's, and then you won't have to deal with a negative in your problem. All right, so now I'm down to 3x plus 7 greater than or equal to negative 8. Got to get rid of the 7. 3x greater than or equal to negative 15. Dividing by 3, x is greater. Oh, I better be careful here. I'm going to actually show this dividing by, because it's not. If I divide or multiply by something, I got to be careful about whether I should switch the sign or not. Should I switch the sign or not? No, because I didn't use a negative. So even though there's an answer that is negative, I did not have to switch the sign. All right, raise your hand if you had that one right. Okay, good. Now on this other one, surprisingly enough, you'd have to divide by a negative to solve it, and then you'd end up switching the sign. I think we can save time by not doing that. I think you're smart enough to handle that. Okay. Graphing linear inequalities. If I was going to graph this thing, you graph it like a normal equation. Act like this doesn't have a greater than or equal, it's just that it has an equals. Okay, if I was going to graph that, I'd start by going to the negative 3 and having a slope of 2. So here's negative 3, and having a slope of 2 means rise 1, or rise 2, run 1, rise 2, run 1, rise 2, run 1, and then my answer is right through there. Okay, now, I just graphed the equal to part. Now I got to handle the actual greater than or equal to. So do I shade above it or below it? Above it. If it says greater than, you shade above. That's all there is to it. Now I recommend you just shade lightly like that, that you don't like darken in the whole thing, because where we're going with this is you're going to end up with problems where you'll shade in one equation on this side of the line, and then you're going to have another equation on the same graph where you shade like on this side of the line, and then you'll have like a third equation on the graph, and you'll shade like above that one, and then you'll have to look where they all intersect. Well, if you've really made the thing all super dark on your first shading, it's hard to see where stuff intersects. This one overlaps in here, and then you save the super dark shading for where a whole bunch of things overlap. Okay, and that will be called a feasible region. It's just kind of a sneak preview of where we're headed with this. But you got to be able to handle the individual lines first, of course. I know you've done this before, so it shouldn't be too bad. All right, now, one thing, this line could have been a dotted line if something else had happened. What would have made it a dotted line? Yes, sir. You got it. If it had just been greater than. up 2x minus 3. This sign here determines whether or not it's a solid line or not. Why? Because the numbers that are on that line either work or don't work. Let's talk about that for a second. So on this graph, if I grab this point right here, 0, 0, it's on the shaded inside. So what does that mean about the point 0, 0? It should work. That's the point. Is 0, 0 should work. 0 should be greater than or equal to 2 times 0, which is 0, minus 3. Is 0 bigger than minus 3? Yes, it is. So it works. Things over here shouldn't work. If I go to like 4 comma 0, x is 4, y is 0, it better not work. Is 0 greater than or equal to 8 minus 3? Is 0 greater than or equal to 5? Is it? No, it's not. It didn't work. That's why it's not shaded over there. Okay? All right. So what about points that are right on the line? Points that are right on the line will work if this is an equal to, and they will not work if it's like a less than sign. That's why you shade it or don't shade it. But if that doesn't make sense to you, just get some way to remember it. Like if it's ever just doesn't have the straight line under it, then it's not a solid line. Or the ones that have a straight line here are a solid line because there's a solid line in it. I don't know. Remember it however you want to remember it, but that's why it's that way. Okay, here is one, and it's not solved for y. You could just start by solving it for y, but I want to make sure you understand there's another way. It's true you could just solve it for y, and then it would be down to y is less than or equal to like 3/4 x minus 12 or whatever. You can do that, but if you want to, you can make an xy chart like we were doing with those parent functions and graph it that way. I want to do this one with you because it actually works out pretty well this way. So everybody, please write that problem down and then make a little xy t-chart next to it. Okay. Now I'd like you to think of some numbers where if I put in this combo of x and y, that 3 times the x minus 4 times the y would be less than or equal to exact. In fact, we want it to be exactly equal to 12. So what combo could you put in there? What number could I put right there that would make it 12 right off the bat? Yeah, and so it would be x is 4 and y is what? 0. So 4, 0 would work. Or what number could I put in here that would work right off the bat? -3. If y was -3, then what would x have to be? 0. What did I just find? The x-intercept and the y-intercept. The x-intercept is where y is 0, and the y-intercept is where x is 0. And so if I graph those, over 4, up 0, and over 0 and down -3, see how they're the x and the y-intercept? If I just draw a line through them, I've got my graph. It'd be smart, though, to take one more point, like try to find one more point besides these two, and just verify that it's on the straight line. If all 3 points line up in a nice straight line, then you're probably doing it right. So again, you give me one more combo here and here. Okay, let me try it. If I stick in 2, -1. So I stick in a 2 here and a -1 there. And I want it to actually be equal to 12 for the graph of the line. Okay, so 3 times 2 is 6, minus, and 2 negatives make it positive, 6 plus 4. Dang it, that's close, but it's not it. All right, -4 and -6. 3 times -4 minus 4 times -6. Is that equal to 12 or not? 3 times -4 is -12. And positive 24 makes positive 12. Good job. So -4, -6. So x is -4. And y is -6. Congratulations, you went off the page, but that's okay. You see how they line up in a straight line? All right. So there's my graph. Should it be solid or a dotted line? That thing tells me solid because it's an or equal to. And the last thing is, should I shade above it and below it? Now, that's the problem with not solving it for y, is you don't know which way to shade it. But you can conquer that by understanding what it means. This point 0, 0, if that point works, then I should shade on that side. Do you see what I mean? I could pick any point and see if it works. Like I could pick this point right here, see if it works. And if it works, I should shade on that side. But 0, 0 is the easiest point of all, so I'm going to try sticking in 0, 0 and see what happens. 3 times 0 minus 4 times 0 is less than or equal to 12. Does that work or not? It comes out to 0 is less than or equal to 12. Does that work or not? Yes. Now I know some of you are thinking it didn't work because it wasn't equal, but it's really, now I can use the less than part, and 0 is less than 12, so it worked. So I should shade here, and if I shade here, I should shade everywhere on this side of the line. Okay? So I know which way to shade that way. And now a lot of you are just going to solve it for y and graph it that way. That's fine. I just wanted to show you an alternative way. More than one way to skin a cat. It's really a disgusting saying, isn't it? I mean, why do people want to skin cats in the first place? Mount them on the wall. Nice. All right. I'm a cat lover. I am. I didn't used to be. I used to be only a dog person, but then I got this cat. Just so friendly. Just loves to like jump up on you and get patted, and just like super friendly cat. Because the kind of cats that I'm used to are the kind that like hiss at you from the corner and like, what are you doing in my house? Kind of thing. Like someday I'll be ruling over you when cats take over the earth. But my cat is really nice. So I got a new respect for cats. All right. I'm going to divide by 4 here, and what would I get? Y is greater than or equal to 6. Well, how do I graph that? There's no x. It's a line. Okay, so I'm going to go 6. 1, 2, 3, 4, 5, 6. Yes, there's y is 6, and it is confusing whether it's vertical or horizontal. I think if you think about it, it has to go this way, because if it went the other way, it would be right on the axis, which wouldn't make any sense. Now, where should I shade? Above or below? Yeah, it's still an above or below question. So it's greater than, I shade above. So there we go. That's how that one works. You get that? All right, how would this one be different? Well, I'm not going to be able to shade above or below it. First thought is, once I divide by -3, what's my answer? Greater than 5. And here's 5. Which way should I go there? Up, down, or left, right? Up, down. And now, how do I shade above or below that? I can't. But where do I shade? It says greater than. These are the numbers greater than 5. Okay? Say that again. Oh, ooh, you got me. Should be a dotted line. Thank you. Yeah, you're absolutely right. There. Now it's a dotted line. Okay. Any questions on that? Well, really, the only other thing we got to talk about then is substitution and elimination, which we talked about briefly. There are key algebra skills for solving systems of equations. Remember how I said it a minute ago that we're going to be heading towards this, where you're going to graph like one line and shade above it, and graph another line and shade like above that. Well, you got multiple equations there. Well, what happens when you have multiple equations is you can find out where they cross. So if I've got this equation and this equation, I can find out where they touch. How do I do that? Well, I can graph them and see where they touch. Or if I'm not going to graph them, I can solve it with substitution or elimination. I would like for you to write down these two equations on your page. Now it says substitution. That means I want to substitute one thing in for another. Wherever I see, this is the key, wherever I see an x, I can put what? 2y. So I see an x right there. So I could put a 2y there. So all of a sudden, now I've got this equation. 2y minus 3y is equal to 14. Doesn't that get it down to just y's? Yeah. It's going to be negative y is equal to 14. I got to figure out how to solve that. Multiply by a negative. Doesn't switch a sign because it's an equal sign. You can flip it around and make it a backwards equal sign. But it's the same thing. And it's negative 14. All right. So now what? Is that the answer? It's half the answer. It's the y part of the answer. I now know the x part because I want something comma something. It's a point where they intersect. And the y of it's negative 14. That much I know. Now I got to figure out the x of it. So I stick in the y is negative 14 there, and x must be negative 28. All right, that's called solving using substitution. You take this fact and you stick it into the other equation. All right, I want you to try one just like that. 3x minus 2y equals 10, and x minus 4y. No, it's too complicated. Let's keep your life simpler than that. X minus y equals 4. We want to see where those two lines cross. Use substitution. Right now, wherever I see an x, I could put what? Well, I got to solve it for x then. Yeah. X would equal 4 plus y, right? And now I can do that substitution thing. Put that into the first equation. So I'll do that in blue. 3, and then I'm putting in 4 plus y here, minus 2y equals 10. And now I'm going to rewrite that down here. 3 times 4 is 12, plus 3y minus 2y equals 10. And that's 12 plus y equals 10. And I subtract 12 from both sides. Y equals negative 2. Did you get the same thing as me? Good. Then I can just finish it by saying if y is negative 2, what would x have to be? 2. 2 minus negative 2 would be 4. So x must be 2. X equals 2. My final answer is 2 comma negative 2. An x and a y that solve my equation. This point would be on this line. And this point right here would be on this line here also. All right, that's how to solve with substitution. How about elimination? Somebody asked me about that earlier, and we practiced it before I even started the video, so I'm going to do one more for the people at home. If I wanted to get this one to eliminate one of the variables, right now I can't add these together because they're, well, I could, but it wouldn't make anything drop. I would have 7x plus 3y equals negative 8, and that just doesn't help because I haven't dropped a variable or eliminated a variable. So instead, on the top, I should do what? Multiply by negative 2. And if I do that, I have negative 4, negative 2, and I multiply this by negative 2 makes positive 4. So now these guys will cancel. These guys turn into what? X equals negative 2. And I'm done with half of it already, and now the other part's really easy. I got to find y. So I go stick that x is negative 2 into either one of the equations. It doesn't matter. I'll use the bottom one because there's more positives in it. 5 times negative 2 plus 2y equals negative 6. And then I get negative 10 plus 2y equals negative 6. And then I add 10 to both sides. And that's 4. And y must equal 2. So it's negative 2, comma 2. Raise your hand if you're comfortable with that stuff. All right, good. Then we're done talking about it. Now, some of you are still like, I really didn't get what you were saying, but I don't want to embarrass myself by admitting that right now. Well, then just ask me during work time how to do it, and I'll help you. All right, so got a worksheet on that. While you're working on that, I'll start calling kids up, telling them their scores on the quiz.